In this module, we will see the remaining part of the matrix algebra that was covered in the previous module. Here mainly we will focus on the inverse of a matrix. Not only in general, in inverse, but also the G inverse, for the singular square matrix, and then how to solve the linear system of equations through matrix inverse. Then eigenvalue, eigenvector, the singular value decomposition and the use of the singular value decomposition, the Cholaski decomposition and the use of Cholaski decomposition. We have seen the basic concepts of matrix and linear algebra in R up to multiplication that we have seen, and we have seen how the different derivation can be done using matrix and vector algebra without using any loop, nested loop in R. Now we'll move to some other aspects of matrix algebra. Is the inverse of matrix, which is a very important part for linear equation solving. So in general, the inverse of n by n, for inverse it has to be a square matrix, as you know. So in general, the inverse of an n by n matrix A is the matrix of B, the another matrix B that is also n by n order, which then multiplied by A gives the identity matrix I. That is, if A is a matrix and B is a inverse of the matrix, then A into B, the matrix multiplication, A into B should give you, or B into A should give you the identity matrix. Then we will say the B is the inverse of A. That is the general concept that you must have learned. So let's assign a matrix, say A, say 2 by 2 matrix, 1, 3, 2, 4 is arbitrarily I assign, and number of column equals to 2. By row it will do. So if you say by row, then what it will do, it will first assign 1, 3 as the first row and 2, 4 the second row. If by default it is column wise, so it would be, if you don't pass anything, or by row equals to false, then it would be 1, 3 one column and 2, 4 another column would be combined. So as here I mentioned, by row equals to true, so the matrix would be first row should 1, 2 and second row should be 2, 4. Then to get the inverse of the matrix, there is a function called solve, SOLV, all are lowercase. So solve function can be used to get the matrix. Actually solve, normally you will have 2 arguments. The solve is developed for basically solving the linear equations. So you can say 2 arguments, but if you avoid the second arguments, it will generate the inverse of the matrix. The first argument should be a square matrix, and then you can just write, say B equals to solve A, and if you just type B, you will see the inverse of the matrix. And just to check whether B is the matrix of inverse of A or not, you can write A multiplied by B, matrix multiplied by B, then you will see that it is actually a identity matrix. Solving system of equations, linear equations, is very easy when you know this vector and matrix concept, because the linear equations can, when you solve the linear equations, definitely you need the matrix algebra. Say suppose, or otherwise you have to do one by one manually by replacement method, that is so tedious. So say mx equals to z is a linear equations. So x, we have to solve x, say. So m is a matrix and x is a vector. Similarly, we have to get the solution of that vector, and z are the vector, x and z are the vectors, and the solution of x should be m inverse z. M definitely inverse should exist. That means determinant of m should not be 0. For illustration, say assign one matrix A is a number of 2 by 2 matrix C1, 2, 3, 4, and n column equals to 2, and B, say the C equals to 7 and 10, so B should be 2 by 1 order vector, so 7. Then if you want to solve the x, what you can do, the solve A, then vector matrix multiplication into that is B. So that will give you the solution of X, that is here 1 and 2. Alternatively, as I mentioned, you can pass the A and B together into the solve function. The solve is within solve you just first should be the matrix A and second should be the B. If you pass separated by comma, it also give you the solution. You don't need the multiplication that I have shown earlier steps. So it itself solve the X. Now we'll see how we will get the generalized inverse. As you know, where the square matrix, the square matrix is singular, you cannot calculate the inverse. There you can opt for a G inverse. Not all square matrices have an inverse, as I mentioned, only those of a full rank. However, all matrices have an infinite number of generalized inverse. A generalized inverse of a matrix A is a matrix AG inverse satisfying this property, that is A into AG inverse into A should be A. That is the concept. If AG inverse is a G inverse of A, then AG inverse into A should give you A. So now I am taking a help of the library mass and then assign a matrix 2 by 3 order matrix using the rbind command, say rbind C1, 3, 2 and C2, 8, 9, then it will generate a matrix of A. And if you pass this assign matrix within a bracket, it will automatically display. You don't need to display the matrix, you don't need to type again A. This is the concept. And the generalized inverse of A is just GINV. So is a function from mass, you will get that mass package you will get. So GINV is a G inverse. If you just pass the matrix, a singular matrix within G inverse, function G inv, it will give you the G inverse. Let's check whether it is the G inverse of A or not. So let's first multiply A by the G inverse of A and then multiply G inverse by A, and then finally A multiplied by G inverse multiplied by A, and see whether it is giving the same matrix or not. Yes, after multiplication we can see it is the same A matrix that we assign. So definitely G in A, that is the new matrix that it has generated, is the actual G inverse of the singular matrix A, the 2 by 3 order matrix, singular matrix A. Now another aspects that you can derive from the matrix algebra is eigenvalue and eigenvector, which is very, very important in many aspects, especially for the principal component analysis, the factor analysis sections. That eigenvalue and eigenvector is a very important concept to solve the to get the solution. In linear algebra, an eigenvector or a characteristic vector of a square matrix is a vector that does not change its direction under associated linear transformation. In other words, if V is a vector that is non-zero, then it is an eigenvector of a square matrix A if AV is a scalar multiple of V. The conditions could be written as the equation AV equals to lambda V, where lambda is a scalar known as the eigenvalue or characteristic value associated with eigenvector of V. I just tried to just recall the eigenvalue and eigenvector concept you must have learned long before. Say here I am assigning a new matrix, say A, 3 by 3 square matrix. Say just arbitrarily I just took the sequence 1 to 9 and then split it into 3 rows and 3 columns. So that A is a matrix of 3 by 3 of order 3 by 3, and then eigen is one function. If you pass the square matrix within the eigen function EIGN or a lowercase, then it will give you the value and vector. The this is the first one would be the eigenvalue, and the second one will give you the eigenvectors. So the square root of a matrix by diagonalization. Suppose n by n matrix A is diagonalizable if there is a matrix V and a diagonal matrix D such that A equals to VD V inverse. This happens if and only if A has n eigenvectors which constitute a basis for C to the power n. In this case, V can be chosen to be the matrix with n eigenvectors as columns, and thus a square root of A is R V S V inverse, where S is any square root of D. As D is the diagonal elements, just take the reciprocal of the diagonal elements, will give you the just get the square root of the diagonal element, will give you the square root of D. Suppose D is one matrix, is a three diagonal, suppose assign a matrix D of 3 by 3 order, then eigenvalue and eigenvector can be generated by eigen within bracket D. If you pass, then say EG, then EG vector into square root of diagonal of EG values, that is the eigenvalues 3 by 3, it will give you a 3 by 3 diagonal matrix, and then transpose of eigenvectors. And if you are confused, you can just display one part separately. Suppose first you see what EG dollar vectors giving, second you see whether diagonal of EG dollar vectors 3 by 3 gives and what the square root of that gives, and then you can multiply. That might give you the clear picture what actually I did here, that by splitting up the steps for this calculation. But this is very important. The square root of a matrix sometimes is required for different computation for a simulations and statistical estimation techniques. Next we will see the singular value decompositions. Let A be an m by n matrix, then we can write A equals to U sigma V inverse, while U is an m by m orthogonal matrix, V is an n by n orthogonal matrix, and sigma is m by n matrix whose first R diagonal elements are non-zero singular values like sigma 1, sigma 2, dot sigma R of A, and all other entries are 0. The columns of V are called the right singular vectors, and the columns of U are called the left singular vectors. See, A equals to matrix 1 to 12, 4 and 3, then this is a 4 by 3 matrix. For singular value decomposition, there is a function called SVD. If you pass the matrix A within SVD, it will give you the U, V and sigma matrix as it will give you D and then U, then V. So D as the diagonal elements only, so you can form the diagonal matrix, and U is U and V, U is the left singular decomposition value, and the V is the right singular vectors that you have in matrix. So D, U and V would be generated by SVD function. We can use this singular value decomposition to get the pseudo inverse of a matrix. So now the next illustration would be how to derive a pseudo inverse by singular value decomposition. The singular value decomposition can be used for computing the pseudo inverse of a matrix. Indeed, the pseudo inverse of a matrix M with singular value decomposition M equals to U sigma V inverse is the M, the plus is a pseudo inverse is equals to U then sigma plus pseudo and U inverse. So where sigma plus is the pseudo inverse of sigma, which is formed by replacing either the non-zero diagonal entry by its reciprocal and transposing the results into the matrix. So that means as a sigma is a diagonal matrix, so pseudo inverse would be just take the reciprocal of all the diagonal elements and that you will get the sigma plus. So that easily, I mean by this equation easily you can get the pseudo inverse of M, that is M plus. So let's see how you can get in R. Suppose M equals to is a matrix of 1, minus 2, 4, 0, 0, 6, 0, 0, 1, 3. Then you can see the determination of this matrix is actually 0. So this 3 by 3 matrix determination is 0. So you cannot get that normal inverse of the matrix as determination is 0. So it's a singular matrix. To get the pseudo inverse, we will first use the singular value decomposition function to get the singular value decompose, because you need U, V and sigma. So let D is the diagonal of SDV $D and 3 by 3 matrix, where SDV $V then multiplied by D and then multiplied by transpose of SDV $U, and that will give you the pseudo inverse of M matrix. Here M matrix. So next we'll see how to get the lower and upper triangular part of a matrix in R. Suppose M2 is a matrix of 4 by 5 order, and if you just pass that M2 matrix within the function lower dot try, if you pass, then you will give a binary matrix where you will have true and false, true or false. Wherever true, you can easily convert as 1, and wherever false, you can easily convert as 0. But by default, off diagonal, if you want include the off diagonal, the diagonal elements, you should specify, and then easily you can get it. Suppose M2, the lower dot try within bracket M2, wherever yes, true, you put not available. Then if you put not available, automatically the lower triangle would be not available, upper triangle would be retained, and that would give you the upper triangular matrix. Similarly, you will get the lower triangular matrix. Instead of upper triangle, you can set instead of setting not available in the lower triangle, you can set the not available the upper triangle. It will give you the upper triangular matrix. And if you want to the diagonal elements off, then you can just say diagonal equals to 0 to true, and then the diagonal would be included as true, and you assign not available. They are true for not available, so assign not available, automatically the diagonal would be eliminated, only the upper triangle would be displayed. The last topic that I am going to cover here is the Cholaski decomposition. The Cholaski decomposition of a Hermitian positive definite matrix A is a decomposition of the form A equals to L prime, L star here say, where L is a lower triangular matrix with real and positive diagonal entries, and L star or L prime denotes the conjugate transpose of L. See, A is again I am assigning a 3 by 3 matrix for the demonstration by the matrix function, and the Cholaski for Cholaski decomposition you just use the function chol, that if you just pass the matrix within the chol function, it will give you the Cholaski decomposition, or that means it will give you the L, and you can get easily the conjugate transpose. Say for solving linear system of equation by Cholaski decompositions, the application of Cholaski decomposition. The Cholaski decomposition is mainly used for numerical solutions of linear equations, say Ax equals to b. If A is a symmetric and positive definite, then we can solve Ax equals to B by first computing the Cholaski decomposition A equals to L star. Then solve Ly equals to B for Y by forward substitution, and finally solve L star X equals to, that is the conjugate transpose, L star X equals to Y for X by back substitution. So for illustration, let A equals to a 3 by 3 order matrix and B is 3 by 1 order vector. Arbitrarily I assign here, and then say assign all the elements in a matrix A of 3 by 3 order, and then B as another vector, say 5, 21 and 15, and then we'll get L as the transpose of the Cholaski decomposition A, that is the L is the T of CHOL A, and that would be the L, and then L prime would be the L star. So first we'll see Y equals to C, we had not assign one array, and then Y1 equals to B1 by diagonal of L1, the first element, the element of the diagonal value, and then Y2 is in this equation that you can solve it, and Y3 equals to B3 minus L31 into Y1 minus L32 into Y2 divided by diagonal L3. Then it will give you the Y. So we will get the Y. So next we will say U equals to T of a transpose of L, and now to get Y we can easily, Y is already there, so we can now solve X in the same way that we did earlier by the back substitution method, and x3 equals to y3 by diagonal u3, and x2 equals to y2 minus u23 into x3 divided by diagonal u2, x1 equals to y1 minus u12 into x2 minus u13 into x3 divided by diagonal u1, and that will give you the solution x, and x can be displayed type x, that will give you the solution. So that is a small illustration for the use of Cholaski decompositions. I mean, this is sufficient to get the idea about the vector and matrix concept in R. So in this module we have learned how to get the matrix inverse, inverse of a square matrix, as well as the G inverse where for a singular matrix, and the eigenvalue and eigenvector, how it can be derived in R, the application of eigenvalue and eigenvector in statistical computation, the singular value decomposition and its application in statistical computation through R, the Cholaski decomposition and its application through the statistical software R. I mean, I think this module along with the previous module really will help you to get a complete idea about the use of linear algebra, that is vector and matrix concept in statistical computation, that really make the computation very faster and easy.